Our next topic of discussion is enthalpy. Enthalpy focuses on the heat transfer between the system and the surroundings. Before we do that, though, we do want to talk a little bit about the work component. Remember the change in internal energy is equal to Q plus W. So just for a moment, we're going to talk about the work component of this. Now, most reactions that we'll be working with that happen in nature happen at atmospheric pressure. And so the work part of a reaction, the work component, usually is just either the system pushing the surroundings back or the surroundings pushing in on the system. Take, for example, the reaction between zinc and hydrochloric acid. So in this reaction, hydrogen gas is produced, which would cause the piston over on the right here to rise up. So in essence, what we're doing is we're pushing the surroundings out. We're exerting a force on the surroundings over a particular distance. So we're doing work on the surroundings, which means the system is losing energy due to that. To determine the value of that, we're going to use the relationship that work is equal to negative P times delta V. So this is assuming that the gas is expanding against a constant pressure. The delta V, remember anytime we have delta, it's V final minus V initial. So if the final volume is larger, that means that the system has done work on the surroundings. So this is why we have the negative sign in place here, because if the system does work on the surroundings, then that means that the work part of the equation, delta E equals Q plus W, that W part needs to be negative if the system is expanding against the constant pressure of the surroundings. Now, if we take our equation, then we have delta E equals Q plus W. If we're at constant pressure, so if we're at constant pressure, then Q is going to be given the value that we call enthalpy, or delta H. W, as we recall, is equal to negative P times delta V. So we get delta H minus P delta V. And then rearrange this equation, we get that the enthalpy, delta H, is equal to delta E plus P delta V. So the enthalpy, delta H, is equal to the change in the internal energy plus the work that's done by the system. In most situations, the P delta V part here is rather insignificant. So from a general standpoint, we can, for most of the reactions that we'll deal with, we'll assume that delta H, the enthalpy, is approximately equal to the change in the internal energy. So getting down to the chemistry of this, if we look at the enthalpy for reactions, we would have our delta H for a particular reaction would be equal to the enthalpy of the products minus the enthalpy of the reactants. Now, enthalpy is a state function, so it doesn't matter how you got to that particular situation, the enthalpy is given a certain value. Now, it's also one where we do not have an absolute enthalpy. So we're always looking at the relative enthalpy. Did it increase? Did it decrease? And so if we take, for example, the reaction of hydrogen gas with oxygen gas to produce water in the gaseous state. The delta H for this reaction is equal to 483.6 kilojoules. And this is an exothermic reaction, so it's going to be a negative value there. So this is a fairly significant amount of energy that's given off. So this is the amount of energy that's given off per 2 moles of hydrogen reacting with 1 mole of oxygen forming 2 moles of gaseous water molecules. Now, if we were looking at this from the standpoint of the beginning and final energy, let's take a look at what that chart would look like. We see in this diagram the energy level of the products up here, the hydrogen and oxygen gas, and our product down here, water. In this case, it actually is water in a liquid state. So the difference between these two energies would be the change in the internal energy for the stoichiometric amounts that would react to form there. If this were water gas that was being formed, how do you suppose the delta E would compare? Would the delta E be higher or lower? So think about that for a moment. Let's consider another combustion reaction. So here's the combustion of methane. So we have our reactants here forming our products here. Although in this case we're given the values for these things. Going from the methane and the oxygen to carbon dioxide and water, the delta H is a negative 890 kilojoules per mole. Notice that if we were to go the other way, if we were to go from the carbon dioxide and the water back to methane and oxygen, we would have to put in 890 kilojoules per stoichiometric amount. So these are going to be values then that we'll be able to use our stoichiometry for. So for instance, if you burned 12 grams of methane and you needed to figure out how much energy was going to be given off, you could use these values, the delta H values, just like you would do any other stoichiometry value. So 1 mole of methane would give off, the burning of 1 mole of methane would give off 890 kilojoules of energy. And again, just a final reminder that it is very important that you consider the states of matter of these things. If we were to do this same reaction with the water in a gaseous state instead of the liquid state described here, that would change the enthalpy of that part of it. So it would change the value. So you do need to be careful about the state of matter that these things are in. So we need to do some practice problems with these, and then after we do that, we'll move on to actually measuring how this heat is determined in the lab.